So as you can see, we're starting very high up the periodic table. We're not going to deal with things with lots and lots of electrons because things get a lot more complicated. But we'll look at something, beryllium dihydride, which just has a few electrons to worry about. Now, if we go ahead and draw out the Lewis structure of beryllium dihydride, we can go ahead and predict what the geometry of this molecule is going to be. And so this is the Lewis structure. There aren't any lone pairs present in this molecule. And so we would anticipate that this has a linear structure. Now, again, if we look at beryllium, we only have s orbitals. And for hydrogen, we only have s orbitals as well, right? So hydrogen has 1 s orbitals that are occupied. Beryllium has a 2 s orbital that's occupied. How can we create a linear structure with just these orbitals? Because s orbitals are spherically symmetric, so we won't get something that points along the line. The answer is we don't. We don't just use s orbitals. The 2p orbitals on beryllium are also low-lying in energy, and we can combine those low-lying 2p orbitals with the 2s orbitals to form a hybrid orbital that gives us the right structure here. And so what's going to point along this direction, we'll pick that to be the z-axis, is we're going to have the beryllium 2pz orbital that can combine with the s orbitals on the hydrogen atom. But to do so, we also need to use the s orbital on beryllium. So we're going to form what are known as sp hybrid orbitals. Now, mathematically, the way we do this is a linear combination. So the 2s and 2p orbitals are close in energy. And similar to what we've done previously with combining atomic orbitals to form molecular orbitals, we're going to combine the atomic orbitals to form hybrid orbitals on a single atom. So this is similar idea, but now we're doing a linear combination on the same atom. Same atom. Okay, so what these look like, mathematically speaking, we'll call these a sp orbital, the psi sp. We'll have a normalization constant here, 1 over square root of 2, because we're adding together two wave functions. And we'll have a combination of 2s plus and minus the 2pz orbital. Okay, and again, we're taking z-axis to be along the bonds between beryllium and hydrogen. So we take these two orbitals here. We're going to have a plus and a minus. So if we add them together, we'll get something that where the positives come together, the negatives over here. And with the minus, we'll get the opposite behavior. So now we have orbitals where the orbitals sort of point along the direction of our bonds. We get two sp hybrid orbitals. Not hybrid, hybrid orbitals. All right, and so the other p orbitals basically remain unchanged, and if there were extra electrons, they would go into those to form the lone pairs. And so our actual bonds are going to be between these sp hybrid orbitals and the s orbitals on our hydrogen atoms. So we can get something like this, and we'll get a sigma bond along, this is just looking at, say, the right-hand side. So here's our hydrogen, here's our beryllium. Their nuclei are somewhere around here. And so these will, again, add and subtract. And when they add together, we'll get a sigma bonding orbital. And when they subtract, we'll get a sigma anti-bonding orbital. All right, and then we have the same thing happening on the other side. And with the number of electrons we have, our electrons will go into the bonding orbitals and we'll form our bonds there. And so our electrons become localized into specific sigma bonds between our nuclei. In the next video, we'll look at combining more p orbitals, so getting another different shape, looking at a boron compound.